Um, but yeah, so if you're interested, we can follow that. And other than that, I'm going to go ahead and get started. So this is kind of like, I wouldn't necessarily call it a rite of passage. It's more of a shtick than anything else. But it's something that I kind of recommend trying to sort of cultivate in yourself if you find interest, and if you sort of, especially if you're planning on having anything resembling a career or lifetime studying humans and science and biology and that kind of thing. And the idea is to kind of like have a sense in your own mind of like what the complete story is. Like where do you think things come from, right? We've kind of, a big focus in this course is this sort of like empiricist game of like trying to think about how everything is sort of can be traced back to some kind of empirical measurement. And, you know, while hopefully pretty aggressively emphasizing the fact that those links are always kind of fuzzy and murky at best, the idea of like, you know, I think one of the cornerstones of scientific thinking is the idea that you're not allowed to believe things without some kind of a reason for believing it. In your daily life, you absolutely are. You can think all sorts of things, and they don't have to be particularly grounded. But in the scientific sort of part of life, in particular in the world of scientific communication and research, the idea is that everything has to be grounded in some way. So this particular slice of the large-scale cosmological story of human existence is my attempt to sort of like cohere everything that I know about those stories into something that resembles like a coherent narrative. We're going to be touching on topics which I am very far from an expert on, like expert enough to teach a class like this, but one of the things that happens when you start becoming a professional researcher is you start to realize the difference between being familiar with a topic, being an expert in a topic, and being like a real expert in a topic. And these are topics which I am sort of at best quite familiar with, but good enough to get started. So, first things first, Big Bang. Boom. That's where, as far as we understand, and as far as we sort of currently believe, we with a capital W, meaning humans as a whole, that's where we believe things started, or at least that's the beginning of the story that we can tell. Big Bang is our current cultural preferred creation myth. And like all good creation myths, it explains a lot of the data. It explains as much of the data as we can explain, but also like all creation myths that have come before, it really doesn't explain everything, and it's not a fully coherent story. Like in ancient Japan, there was a myth that Japan was formed by a god who stuck a sword into the water and pulled it out, and the droplets form the islands. That's a pretty good story to help you understand like where to find more islands. Like if you go west, you're not going to find any. Or east, I guess, you're not going to find any. If you go west, you find a big landmass. If you go down southwest, you're going to find a big string of islands. So it's useful in that regard, but it's not particularly satisfying from a sort of geological perspective. Similarly, a lot of the Western tradition is based off of the cosmology of the Bible, which we don't really tend to think about in the beyond the sort of let there be light aspect of it. But if you go back and read just like the first like 150 words of it, it's based off like, it's a more ancient kind of Hebrew cosmology that like we're kind of like living in a bubble in a giant ocean where there's like an infinite ocean, and then the stars form like a dome, and then we're like this like crust of Earth floating on an infinite ocean, and the fixed stars are the thing that's holding it up. And that was kind of enough to explain why there are such a thing as fixed stars, which we know now are not fixed, they're just really far away. And there's these other things called planets that kind of zip around on the inside, which we used to think were part of like these spheres and inset on each other. Again, sort of a lot of stories that helped us to sort of make sense of the scientific data that we had. But I'll bet if you were to sit down any of the sort of scholars of the time and really sort of ask them, like, how certain are you that this is the full story? I would hope at least that they would give you an answer at least somewhat similar to what you would get from a modern cosmologist. who would say, well, it's almost certainly not true, that story that we tell. And we know that it's not true because everything we've thought before has also been proven to be not true. And everything that we continue to learn causes us to continue to reshape that story. With things like the Big Bang, it explains why if you look out, you see expansion in all directions. And if you sort of like roll the clock back of something that's always expanding in all directions, you eventually get to a place where it's in a small, compact space, and then you can do all sorts of more specific, complex, global scale scientific efforts involving such things as radio telescopes on the Earth and on the top of mountains and in low Earth orbit. I guess not so low Earth orbit anymore. And you can tell all sorts of stories that make sense, but in the same way that the sword in the water doesn't really explain everything there is to know about Japan, the Big Bang also doesn't explain everything there is to know about the universe. There was just some PopSci article about some recent modeling discovery that the data might make more sense if we give up on the concept of the conservation of energy, and that might sort of explain the data better, which would seem like kind of a big trade-off, but we've actually given up on that before when we started moving towards relatively, well, that's not really true, but anyways. Point is, if you want to tell a story that's grounded in empirical research, it's typically going to start with something like the Big Bang. The Big Bang was a massive explosion where, PopSci stories of the past couple of weeks notwithstanding, all of the energy in the universe was made available at that time. So the story, as far as I understand it, is that in those sort of initial moments of expansion, everything was there, including a bunch of antimatter and a bunch of matter, however you want to define those things. I'm not really there, which, when put into contact with each other, obliterate themselves and are replaced with the equivalent E = mc squared of energy. And that sort of initial obliteration of matter and antimatter is thought to be the source of all. You okay? You still look like you're fighting for your life. You're doing great. Yeah, so that sort of is the source of all the energy. Most of that explosion turned into light and heat and things like that. There was not such a thing yet as chemistry. We'll get to that in a bit. But in one of sort of the first, perhaps sort of oldest by date scientific mysteries, whatever obliteration happened in those first picoseconds of the universe was not symmetric. There was, after all the matter and antimatter obliterated itself, there was some stuff left over, which is very convenient for us because that's everything that we know and care about. And it's some of the oldest, not oldest, because actually relatively recent, but there's strange math of symmetry breaking physics, which is trying to understand why there was something left over after that initial obliteration and stuff. Emily Noether is a name there, who also has sort of the historical interest of being a female physicist from way back before that was cool. And there's some strange stories of like scientists you've heard of, like Einstein, like cheating universities to sort of trick them into hiring her. And she did a bunch of early math of symmetry breaking physics. Anyway, so after those first picoseconds of expansion, all of the energy that we could ever care about, as far as we know, is created. And then for a period of time, which I'm actually not familiar on the exact amount of time, that's all that there was. Just a bunch of plasma and extremely hot gas, which was too hot to do anything that we would think of as a gas. And as that expansion expanded outwards, the universe cooled off, as things tend to do. And slowly but surely, the initial stuff of the universe started to coalesce. And the coalescence, I think the first thing that formed that we would recognize was this, things like the quarks and the protons and the electrons, and then our very first good friends named hydrogen. I'm going to slowly but surely, actually not that slowly, we're going to sort of quickly, what's the word? Periodic table. If we want to talk about the history of biology, you kind of do have to start with the Big Bang, because the Big Bang is how you explain why you have such a weird thing as this. This is also a nice approximation of true, a very useful sort of configuration of letters, which have a lot of meaning associated with them. And as far as the story that we're telling, we've just reached here. And the hydrogens form at some point in the history of the early universe. I should know that number. Maybe next year I will. But slowly over time, those gases cool down, and you get such a strange thing as a nebula. A nebula is just a big wad of gas floating through space. The nebulae form because there's such a strange thing as gravity, and gravity is something that pulls matter together. And so if you have this sort of bunch of random stuff floating through the universe, and there's nothing else going on, and they're slowly, heat makes things zip apart from each other, gravity makes things pull towards each other. Turns out that's a pretty important distinction for the rest of the time that will come. And so as the universe starts to cool down, the particles start to pull in on themselves. They form big clouds called nebulae. And eventually, you get enough of these gases together. And I say gases, but really there's only one gas at this point. It's hydrogen. There might be, I don't even think there's helium yet. I think it's just hydrogen. And there gets to be enough of it that the gas pulls in on itself even more. The gravity sort of wants to smush everything down into the smallest space possible, until eventually the gas gets so squished down, and as it gets squished, it rubs on itself and gets hotter, and not really friction, but the compression of gravity causes another very important event in the history of our universe, which is the ignition of the first stars. Now, it is really an ignition. And I am going to speed up here because it's important to get to the parts of this that actually have like neurons and stuff like that to make it relevant to the course. But I promise it is at least a little bit relevant. So basically, okay, nice. So you get the big clouds, and they slowly sort of condense down until they become spheroids. And as the gravity is pushing in, the gases are getting hotter until eventually some strange quantum effect happens. It's not exactly like a combustion engine in your car because there's it's like a quantum superposition thing, I guess. But eventually it gets squished together enough that you get a very strange effect called fusion. And fusion is the thing that happens, skipping over some details because I'm not fully aware of them, but fusion is what happens when you get from something that looks like this, which is one proton and one electron, and you get them close enough together that some strange thing happens, and they become something like that, which is our good friend helium. So once that process happens, fusion is an extremely exothermic reaction. So a massive amount of energy is released when these hydrogen form into this helium. And so now the collapsing force of gravity is being pushed back against by the exploding force of fusion, and you have a nice stable star, which is happily burning hydrogen into helium. Good job for that star. Now that lasts for a good little while. And so basically right now, this star, of which if I knew more about stars, I would know the type, but I don't, so let's not worry about it. This star is now burning its fuel, and its fuel is hydrogen. And the output of that fuel, of that burning, is helium. And so that is all well and good until eventually the star runs out of gas. And so now it no longer has more hydrogen and it's nothing but helium. And this force of compression is not enough to fuse helium into lithium and beryllium and guess like that. Some of those details about the elements is going to squish out in a little bit, but good enough for the conversation. And so eventually, when all the helium is gone and the fusion force is no longer fighting against the force of gravity, the star starts to collapse again. And as it collapses, it gets denser and it gets hotter until eventually you do have enough of the force, enough juice to form to start fusing heliums into berylliums and lithiums. You got your ones, you got your twos. Now you can start making threes and fours. That's math, that's chemistry, that's cosmology. There's probably other details involved. I'm sure you guys are taking all sorts of classes in that right now. So now we burned through our hydrogen. We're starting to burn our helium. But this process is also fusion. It is also extremely exothermic, but it is less efficient than the previous one. Helium plus helium equals beryllium produces less energy than hydrogen plus hydrogen equals helium. But that's okay, because we still got this thing. We're now in a new phase of star life. We're burning hydrogen, we're making beryllium, and that all lasts for a good long time until eventually you start running out of helium and you get that same sort of process over again. This is probably like overlapping. It's probably not you do one then the other, but eventually you start getting to a point where the star is trying to collapse again, and then you start getting hot enough that you can start fusing your berylliums into the other kind of weird stuff that comes through. Now this good story works for a good long way, where the best, most efficient reaction you can have is hydrogen to helium, but then as you start, losing that steam, you start getting hotter and hotter, collapsing, until you can start fusing the different elements into heavier elements. And that process works pretty well all the way up to, and I think including, iron. Iron, very useful thing and for daily life, is the first point in this kind of march of chemical complexity where the process of, and I'm just really going to be making this up, I'm not sure if it's a process that makes hydrogen or sort of processes of fusing hydrogen afterwards. This process of fusion is not sufficient to fight against the crushing force of gravity. And so when that happens, the star starts to collapse down even further. And as it's going, basically every time it burns through one of these elements, the time that it takes to start burning the other one and run out gets smaller and smaller. Until by the time you get to hydrogen, to iron, the collapsing doesn't even, it takes you longer to do it, and it also has like the diminishing returns. Like you get less bang for your buck, I suppose, literally. Until eventually, once you get past iron, that explosion no longer stops the clock. Like it's no longer enough to keep the star coherent. And so you get this process where the star starts to collapse in on itself, sort of like chunk by chunk, piece by piece. And every time the outer core collapses, it hits the inner core, it creates another pressure spike. And that pressure spike is where you get most of these other heavier elements, down until you start getting into some kind of like, these may only exist in labs sort of things towards the bottom. And then once all of that sort of, depending on the size of the star and sort of the makeup of the star, this process of sort of burning through the different chemicals and then this final process of collapsing eventually results in an explosion, which is what we tend to call a supernova. And that supernova is when all of these weird, extra fancy, strange, relatively rare chemicals get spewed out into the universe, and everything that we sort of know and care about, all the weird chemistry that does all the cool stuff, comes from this type of a process. And so And the strange thing about this, the part that I find really, I mean, aside from all of it, really kind of troublingly awe-inspiring, is that a lot of the things that you talk about when you talk about space, we're talking about, on the orders of like, millions of years and tens of millions of years, and sort of the process of burning down from hydrogen to helium. This could take, millions, tens of millions of years. This process, after iron, of sort of slamming down and exploding outwards, like 2 weeks, like a star scale of an explosion, like big enough to rip our entire solar system apart, happening on the space of like, between now and the end of the poster presentation. So that's a little troubling, but very useful for biology, because this is where all the good stuff comes. Now, there's a couple things to note here when we're talking about the chemistry stuff, which is that in terms of like you and me, like most of the stuff that we're made of and that we care about tends to live pretty low on that list. So when hydrogens, that's your carbon, nitrogen, oxygen. Like these are really our best good friends. And the fact that they are above this line means that there's a ton of this stuff in the universe. In particular, our good friend oxygen and our good friend hydrogen, carbon too, hanging out, are all over the place. And because of the prevalence of hydrogen and oxygen everywhere, that also means you get tons and tons and tons of water. There is lots and lots of water in the universe just floating around. There's a lot of like stellar processes whose output is just water ice being flung out into the universe. We're reading about this one, star that they were looking at, and they thought that it was emitting trillions of times the water on the surface of the Earth every second for like millions of years. There is no shortage of water in the universe. And all these other guys that hang out around it, your carbons and your nitrogens and your fluorines, similarly prevalent. So that's useful. Another useful guy, where are you? Silica? Silicon. Silica. This is where you get rocks. You get rocks from all sorts of places, but silicates rocky stuff, which is, again, very useful for humans. And so as this sort of strange chemistry is going on, I believe that the time scale of the universe, we're talking like 12 billion years. I think that's the number that we tend to say. I don't really know what these numbers mean. That's one of those numbers that changes from time to time. So, but on that scale, and most of the time of the universe was spent just doing this and sort of getting to the point where we're burning through all these things. And the first, in terms of percentage-wise, most of the universe has been spent doing this stuff. Where are we at? Yeah. So, in terms of our list of things, we've gone from the Big Bang to nebulae to stars, and then the stars started exploding, and that's where you get the weird chemistry, and then the weird chemistry is where you start getting such things as planets. That same sort of process of accretion, where the nebulae turns into stars, and then the stars start to explode and spill their guts out, leads to other types of dust, and then that other types of dust can form into other types of spheroids, some of which we like to refer to as planets. The definition of a planet is a complicated thing. It's not that complicated, actually, I just don't want to talk about it. But we, for our purposes, can just think of it as any rocky spheroid that orbits a star. And of course, all of our, well, maybe not these days, but certainly the most useful planet for humans is Earth. And Earth showed up at some point in the past and started as a disk of dust around a small yellow star, medium-sized yellow star named Sol. It wasn't named that before we named it, but we did name it, and it's named Sol. And slowly over time, over millions and billions of years, that dust accreted down into a rocky ball, which was mostly at the start of its life, very, 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 very hot. Hot like sort of magma, liquid magma on the surface of the earth. Bad time for complex chemistry. Actually, great time for complex chemistry, bad time for delicate chemistry, which is what we are made of. And so for the majority of the lifetime of the planet Earth, it was uninhabitable, lava town, acid rain, solar radiation, bad times for biology. However, as stated before by these now out of nowhere, I think this one, there's lots and lots and lots of water in the universe. And so of the millions of sort of trillions or quadrillions of tons of dust which accreted into the planet Earth, a good percentage of that was water ice. And slowly over time, that magma ball of dirt that we call Earth cooled down to the point that some of that water was able to stay on the surface of the planet and not evaporate off into space. And so that was the start of the oceans. Oceans are a very, very useful thing for evolution of life because the universe is a rough place. It's mostly empty, but the places that it's not empty are pretty rough. And so if you want to have a process that would allow you to develop complex, delicate biochemical processes, there has to be a way of those processes to be protected from the horrible universe at large. And so in every example of the evolution of life that we have available to us, which is roughly this many, that evolution began at the bottom of a warm liquid water ocean. In particular for us, well, talk about the details in a second. So yeah, warm liquid water ocean, very useful thing for the evolution of life, and at least one example, and if we think about it, probably other ones as well. And if you ask yourself, where is the largest warm liquid water ocean in the solar system, you might think Pacific Ocean, but you would be wrong. The answer is Europa. Europa is or Enceladus, I'm not sure which one. Both of them are moons of Saturn. They are ice planets, so if you look down from the outside, just a shield of ice. But they're geothermically active, so their core is warm. So there is, between the core of ice and the rocky planet, in the middle there's a warm liquid water ocean that we've never seen. But we have flown spaceships through the geysers that erupt from the bottom of those planets, and when we sniff the dust that gets thrown up there, it's got like methane in it. So I'm not saying there's life down there, but I'm just saying I would like to go down and check. Anyway, so now we're on a planet. Don't need any beryllium anymore, as far as I know. I think we use beryllium to make the lenses of thermal cameras because it like can bend the wavelengths of light that you need for that, but I don't need it in my day-to-day life. So here we are now on the bottom of the ocean, and we start to develop all of our great-great-grandparents, which is weird goop. That's where we all came from. And somewhere in the process of whatever's going on down there in the bottom of that primordial ocean, you start to get strange linkages of common molecules, your carbons and your hydrogens and your oxygens and your whatnots. And again, this is a story that changes somewhat on the regular, and I haven't checked in on it in a little while, but my understanding is that we believe that the origin of life started with something resembling RNA. RNA being a self-replicating molecule. So the self-replicating is important, right? Because now because you only need to come across one of these things to have an infinite number of these things. Because if the thing is able to create more of itself, then then you're off to the races. If you're self-replicating, you have the materials for replication and the opportunity to engage in that behavior. Now we've started what we might call biological evolution. So the RNA is out there doing its thing until eventually whatever chemical thing happens. This is where it also, if I was a different type of biology professor, I would know this in more detail. That RNA somehow becomes DNA. The DNA starts to have its own little environment. And we have, this is something resembling this is probably what we would sort of, if we could go back through the timeline and say this is the origin of life on Earth, it would probably be some weird little guy that looks like this. And this little guy has something that's just very, very important, which is an inside and an outside. The inside of this thing is everything that he would call himself, if he has a gender, which he certainly does not. The outside is what it would call everything else. So we have a distinction now between inside and outside. This, if it could speak English, it would say, I am this, and this, all that, is everybody else. So these guys are slithering around for a good while until eventually some other guy decides that, you know what, I might just go ahead and eat you. And so they're going around eating little guys like that. And then he's like, actually, maybe, in some weird conglomeration of factors over the course of millions and billions of years, one of these things eats another one of these things, but the thing on the inside doesn't die. And so instead of dying, it sort of maintains, it sort of says, okay, well, I'm out here and you're out there, and I still don't really care about that. And I have everything that I need to sort of survive my life, and I'm going to excrete things that apparently you need. And as long as we can deal with this, then I am happy and you are happy, and we have now created eukaryotes. Eukaryotes are little goopy things with organelles. We believe that the organelles were like prokaryotes eating each other and then sort of like, making up after that. Anyways, this goes on for quite some time until eventually all the little goopy guys decide to, maybe we should band together and form such things that we might call multicellular life. Now, the first multicellular life, as far as I understand it, were like tube worms. I think that's like sponges and tube worms, because at the bottom of the ocean, all the action apparently happens at geothermal vents. And that's the place where all the weird chemistry on the inside of the planet spews out into the warm liquid water ocean, which is protected from the horrible radiation and sort of what are they called, meteorites of the outer world. And so all this weird chemistry is where we can get the sort of the weird precursors that we need to have that mRNA and whatever DNA and the little prokaryotes and eukaryotes and whatnot. And eventually we form little spires and we just live our happy lives for quite some time as tube worms at some geothermal vent at the bottom of some ocean somewhere on the planet Earth. Again, we are kind of going to be, this is, if you check my work, I'm sure you'll find some places where the story doesn't quite line up with what I'm saying, but in the manner of cartoons, I have done my own due diligence that if you did look up the details and you got those extra layers of specificity, you would understand why this cartoon is the one I showed you and not some other cartoon. And you would say, oh, well, he was missing some of the details. He must not have realized this new research or this subtle factor, but tube worms on geothermal vents under the water is our current best guess of what's going on. Now, at some point in this process, one of these guys has a terrible idea, which is that I think it's time to leave the geothermal vent and move around the world. And if I'm going to do that, I'm probably going to need something resembling a nervous system. So in the sort of Aesop's fable kind of just so story version of evolution of life, one of these tube worms kind of popped off and just became sort of a regular worm. There's a lot of stuff I'm skipping here, but this regular worm There's also different branches of the tree of life where things sort of went off in different directions, and some of these guys became like corals and stuff like that. But the ones that we personally care about, that we have a personal affiliation for, are the Wriggly Wriggly worms. And the Wriggly worms had a very good invention, a really great idea, I think one of the best ideas in the history of life, which is if you're a tube, you're pretty much just a mouth. And so if you're just a mouth, then that's really also, it's a single purpose entry exit point. You have an inside, you have an outside, and that's about it. Worms came along and they said, I have a great idea. Let's have that tube go all the way through. And let's separate our concerns. We have input, we're going to call this a mouth. Then we're going to have some other guy that we let things out through, and we'll come up with a name for that later. And this is, now we have worm. Good old worm. When you are in other classes, they talk about C. elegans and things like that. It's these kind of guys. They have neurons. We've had sort of enough specialization for neurons at this point. And they have something that we would call a nervous system because the neurons are sort of connected to each other. But it does take, yeah, and it's, yeah. But there's nothing here that we would call like a central nervous system. Like we don't have spines yet, we don't have limbs yet. We just have something which is capable of sensing the world and then performing actions on the basis of that information. The first sense, arguably, likely, chemosensation. That's the sensation and detection of chemical gradients in the environment. We would refer to that as smell or taste. So if you walk into a room and you smell something, you're picking up on a chemical gradient that is sort of different enough from your regular environment that you're like, oh, there's a smell. It's coming from over there. I wonder what it is. Probably some weird biology, because that's makes volatile organic compounds. And so these little wriggling worms, honestly, that sensation was happening at the single cell part of this story. Like they wriggle towards chemical gradients because that's how they find food. This is also, and actually I think this was also a eukaryote thing. Somewhere in this process, you have the very first beginnings of the evolution of vision, as some things, plankton-style things, start to develop light-sensitive patches on themselves. And those light-sensitive patches, coupled with some kind of a locomotor system, which in the water doesn't have to be very much, it could just be a buoyancy bladder, allows them to float upwards when the sun is out and then sink downwards when night comes. So they can float towards the surface of the water when the sun is out so they can do photosynthesis, whatever they're up to, and then they can sink down into the depths at night so they can avoid, actually I don't even think we had really predators at that point, but light sensitive patches on single cellular organisms, that's the origin of the kind of the weird chemistry I've talked about before, all the opsins, all those like the weird photochemicals in the back of your eye owe themselves to the weird chemistry that developed these guys back here. Yeah. Yes, so here we are now. We have some pretty good stuff. We've got cells, we've got neurons, we've got light sensitivity, we've got some kind of a motor system. We've got a world which is increasingly less magma-y, lava, whichever one. It's like whichever one's on the surface. I can't remember. Lava versus magma. Like it's like one's on the surface, one's below the surface. Lava's on the surface. Yeah. So our world is becoming increasingly less lava, increasingly more ocean. Everything's pretty great. This persists for probably, we're still in kind of the B territory. So we're in billions of years of just kind of like wriggling around as weird goop and worms and tubes and sponges and stuff like that. And then at some point, this is another one that I really wish I had written the number down here. there's a strange event that happens. So we're evolving things like shells and stuff like that, just like structure for our bodies under the water. And then in the fossil record, there's a very, very clear moment where all of a sudden there's life everywhere, and it gets real weird. And that moment is called the Cambrian explosion. So Cambria is like if you're looking through cuts of rock, farther down you go, the farther back in time you are. And there's at some point in this, you just start seeing fossils everywhere. And you get this strange type of rock called fossiliferous limestone. When I was at University of Texas at Austin, Texas used to be the bottom of an ocean, and they have buildings made out of this fossiliferous limestone, just like, big buildings and walls that's just like nothing but thick fossils of, things like bivalves and shells and, strange things like that. And it is thought that the reason for this big explosion of biodiversity, biological density and biological diversity was the creation of what is, if the separation of concerns of the tube is the best invention, probably the worst invention is the creation of predation. Because before this time, I think there was people were still going around eating each other. I think just that's kind of a thing that would happen. But at some point, you start to see the beginning of the predator-prey arms race, where the predators start to realize that, I can actually, I don't have to spend all my time trying to do photosynthesis and all that kind of stuff if I just learn how to eat the things that can generate their own energy. And so I'm just going to start really specializing in all the tools that I need to eat other animals. And other animals become prey, and they say, well, I'm going to have to sort of develop defenses against those predators so that I can go around making my own energy. And then this kind of, again, in the Just So story of the cartoon version of the history of the world that I'm telling you, this sort of predator-prey dynamic starts to really drive the evolutionary process into overdrive. And it is thought that the explosion of biodiversity that happened in the Cambrian explosion coincides with the original development of that predator-prey dynamic in the animal kingdom. Somewhere around this time, this progresses for a while. I believe at this point we're still kind of thinking mostly in terms of bivalves and gastropods and maybe some sort of worm-like objects. Some of those worm-like objects sort of branch off at roughly this time and become the cephalopods eventually. Cephalopods are things like cuttlefish and octopus and stuff like that. Very, very intelligent animals that have a very, very distantly related to us. So they still have things like opsins and stuff like that in their retina, but they don't have a lot of the other stuff that every other animal that has anything we would call intelligence has, because we have this, on Earth, we do have another animal that we can look at that has evolved intelligent life. And it does have, we do have the same lineage at some point, but you have to go real far back to find it. So that's one of the reasons why I have just this deep abiding love of cephalopod neuroscience, because they are the closest thing we are likely to get to studying an alien intelligence on the planet Earth. This is also around the time, somewhat after this time, I don't know exactly when. This is where you start to get a bunch of really weird animals in the floating around in the water. There's you can look them up. There's a lot of weird ones. They got weird antennae, and there's just one it's got a buzz saw for a mouth, and just strange animals swimming around, most of which didn't survive to the modern day. Notable exception being horseshoe crabs, horseshoe crabs and trilobites. They've been they're from this point in time, or sort of around that time. And so in that time, you start to get the creation of another useful thing for humans, stuff like bones and muscles start to show up in the sort of the lineage. And the first one, well, not the first one that I care about, but a skeleton of note are the bony fishes. So those are these kind of guys, bony fish. And actually before these guys, you have the jawless fish. And the jawless fish, I believe, are the first vertebrates. Jawless fish, our modern closest friend. There's a bunch of them, but the most, I guess, common currently extant jawless fish is a lamprey. Lampreys look like this. They're horrible, but they are the earliest, I believe they are the earliest vertebrate chordata animal. Yeah?
Are they super different leeches?
I think they just look like that. I think leeches are invertebrates, but they do have that same kind of like suckerfish look. But I believe that might be, this is getting below my depth of the details, but if I had to guess, I would guess that they probably came onto the scene at around like similar times. But leeches are not, well, leeches evolved to suck blood, so they probably came later. They're a predator. They're like not a predator, a parasite, so they probably came later after there was something to suck blood from. But they do look very similar. And these guys have a spinal cord traveling down them. I don't know if they have bones or if they're cartilaginous like sharks. But they showed up, and they're good friends in some ways. If you go to a neuroscience conference, like Society for Neuroscience, something like that, there will still be big chunks of the poster sort of city that shows up there studying jawless fish and lampreys because they are the oldest, sort of the phylogenetically most ancient available chordata, which is us. Okay, how are we doing on time? Doing okay. Yeah, I'm gonna speed up. Yes, and then at some point after them, you get these guys, which are the bony fish. Bony fish have things like skulls and things like, they have the spinal cord, they also have the spinal column, and they also have things like eyeballs. And so this is around 450 million years ago, quite some time. So whether or not this is the first of this type of thing, or just like the first one to really leave a bunch of fossils, but this is also these are the oldest eyeballs that we know about, that we would sort of call something similar-ish to our own. A lot of things like clams and mussels have eye stalks. They have, photosensitive chemicals and little sort of optical objects. But these guys have proper eyeballs, and in this paper, which is one of my favorite papers ever, they talk about, Mike Land talks about, there's evidence, get out of here. No, this is a book chapter, not a paper. There's evidence that even at this level of evolution, 450 million years ago, these guys probably had eye movement patterns that are similar-ish to our own. They appear to have eye muscles, and they appear to have the sort of the machinery necessary to have something like the vestibular ocular reflex, which is the thing that I've harped on quite a lot about where if you move your head, your eyes counter-rotate, talked about how ancient it was, talked about how old it was, talked about how you can't lose VOR without also being dead. It's this old, at least this old. And the reason, again, in the cartoon Aesop's Fables version of the story, for that is all the same reasons why I said we need stuff like that. Like opsins are slow. It takes a while for them to respond to light, and so if they're going to be able to form an image, they have to have a mechanism for stabilization. And so because these opsins are in the billions of years old, that chemistry has been around for, that's from like goop era. If once you get to the point where you have animals that are forming detailed images of the world, you have to have that coupled with a mechanism for stabilizing that gaze relative to the world. So this paper just sort of goes through and looks at a bunch of animals. The argument of this paper is that all forms of vision, any animal with good vision exhibits this saccade and fixate strategy with some sort of gaze stabilization resembling VOR. And so this is a goldfish. You have gaze, head, and then this is the result. These patterns may look familiar if we're looking at the squiggly lines I pulled up the other week. This one is a rabbit, which is, I guess, not as exciting, but evolutionarily. This is, who is this guy? Oh, Demoiselle crane and a pigeon, talking about that kind of like the head bob motion as a gaze stabilization mechanism. This is a chameleon. This is a rock crab. Now we're getting into that sort of evolutionary depth. This is a stalk-eyed fly. And so all these guys are exhibiting that same kind of pattern of saccade and fixate with some kind of gaze stabilization mechanism. And we kind of jumped ahead in terms of the evolutionary story there, but just pointing out that this is like, we're sort of starting to get into stuff that we have now touched in this course in this topic area. Now, okay, now we're actually not going to accelerate, because we're going to jump ahead, but in terms of like the time that has passed, the time is really going to start to condense here. Because everything I've said before this is probably, this is 450 million years ago. That means everything before this is 11.5 billion years, and everything after that is 500 million years. So even as I jump forward by like hundreds of millions of years, we're still zooming in very, very, very narrowly on just the barest crust of history that we are actually a part of. So at some point after these fish, we start to get another good addition. Well, I guess, yeah, so at some point they crawl out onto the land, and they start getting their little hands, and we sort of, hands and feet, we start to develop this particular pattern of tetrapedalism, which is the sort of the general shape of head, upper limb, lower limbs, that sort of, has become quite popular of late. And that's where you get the fish crawl out, because at this point everybody's still living in the water. Plants have made it onto land, but no animals have. So fish start crawling out of the water to lay their eggs because it's safe, and then they sort of get more accustomed to it. Then you get these kind of transitional, like lungfish style guys who sort of like hang out on the borders. Eventually, some of them crawl farther out, and you get the sort of like the reptilian types, and then those turn into the bird types, and then those turn into the mammal types, and then the mammals kind of, and that's when we're going to sort of focus. That's the focus of our current conversation. And there is this very famous animation, Sagan Cosmos Evolution GIF, that So this whole story that I've been talking about of sort of like the evolution, the kind of this whole history thing, is kind of a play on the Sagan version of this, which he calls the cosmic calendar, where he goes through, okay, imagine that the history of the universe is this 365-day calendar. Where were we at these different points of the calendar? If I, maybe in the future, I'll like remember those dates and use that same shtick. But this is, so this is from the show Cosmos, which was just a great show that's, I think, still worth watching. Can you pause, play? No? Are you gonna do it? Oh, you're not the actual thing. Ah. And so this is the sort of the short form story of evolution. Show the whole thing? Yeah. So this is from you get the lipid bilayer, you get the protea, you get the eukaryotes, you get the multicellular guys, you get the sort of the rock polyps, you get these are the geothermal vents. When they break off and become weird worms, they become weird fish. They get these limbs, they get bones, they start crawling out onto the water, they become reptiles, they become the saurids, which are dinosaurs, and then they become these guys. So these guys are the first mammals. And they were basically tree shrews. They were they were little sort of, they were hanging out the same era as the dinosaurs. They were sort of like, they were small, kind of hiding in the bushes type of thing. And then when the cataclysm that killed the dinosaurs occurred, it became a bad time to be a megafauna who requires tons and tons of food to survive. It becomes a very good time to be a microfauna. Particularly one that was endothermic, so we can warm our own blood. Really useful tool. We're going to come back to these guys. And so they become these tree shrews. And so particularly kind of our particular lineage of mammals is related to the tree, like the tree part. So I guess the first ones are kind of more, I think they're more like possum-like was the original mammals, but I could be wrong. But we specifically emerged from the tree shrews that were sort of living in the trees. And that's where you get, they were arboreal creatures, so they lived in trees, which means that because they are arboreal, they are walking around on branches. And because they are walking around on branches, their main appendages are grabby. And so you start to develop, even at this era of evolution, a very tight coupling between the perceptual system and the motor system, because we're squirrels. We're running around on branches. We're grabbing and moving and things like that. So again, in the just so story of evolution, it makes sense that we would currently have such a tight coupling between our perceptual and upper limb appendage system, because we emerged, our locomotor system required us to have a very sort of tight perceptual motor loop. And then we get some more of the stuff which we're going to talk about in some great detail. And then at this point in the thing, he says, these are some of the things that molecules do given 12 billion years of evolution. If you leave hydrogen alone for long enough, it builds radio telescopes and develops existential anxiety. So, congratulations. Okay, so we have made it. We've made it to Earth. We made it to us, roughly speaking. We've gone through that early stuff, the goop phase, bones and spines, evolution of predation, tetrapedalism, mammals, the grabby tree shrew era of life, and then various types of monkeys and I guess apes, which I won't belabor too much of the point there, but But we get to, so around, let's see, I think this is the one I want. This was not the picture. Oh, this one. So, this is ahead of the game here. So in terms of the lineage of extant primates, we don't need to go into much detail there. Basically, there's a bunch of them. There's monkeys, old world monkeys, new world monkeys. It's another little piece of colonialism for your scientific nomenclature. Old world monkeys are the ones that live in Africa. New world monkeys are the ones that tend to live in South America. So old world monkeys is things like baboons. New world monkeys is ones like capsaicins or whoever they are. And then the apes split off from the old world monkeys, and our current cousins are the great apes, of which there are, it's us, chimpanzees, bonobos, gorillas, orangutans, gibbons. I think that's it. And I do need to say this because it's important to me to share. But the there's a big like evolutionary question, like sort of question about like which of the extant apes are the most similar to us, and we all think chimpanzees, but there are also bonobos, and we are equally genetically related to both of those. And it's part of this question of like human evolution of like, where are we more horrifically violent in our nature, or are we more like caring and cooperative in our nature? And the answer is that that's not a well-formed question, because humans are too complex to have that story. But the comparison of us to other great apes is always kind of, I don't know, an interesting comparison there, because in general, chimpanzees are quite violent. They are not as violent as they're often, well, they're pretty violent and quite scary, and they handle things in a very aggressive way. If I had more time, I would talk about Jane Goodall, who is perhaps my favorite scientist to exist. But we're not going to get there. But I have to read this one quote from C.O. Lovejoy that was talking about Ardipithecus ramidus. So Ardipithecus ramidus is the oldest ancestor that we share with the other apes. And it was do we share? Yeah, we do share. It was a grounded ape. So it lived on the ground and yeah, so instead of being an arboreal animal, it was a grounded animal and had Ardipithecus. Anyways, I'm not going to find this. I'm also probably going to wind up spilling over into next class to get some of the details here, because there's running out of time and there's more to say about the actual human part of this. But there's this great paper about Ardipithecus ramidus that was discovered. You know, the bones of this guy was discovered relatively recently. And I gotta find the PDF so I can recognize the thing. And so it's sort of asking that question around like the evolution of bipedalism, the evolution of humanity, and kind of like what was life like for these early creatures, and sort of what does that say about us? And one of the big questions that often comes up is like, were we engaging in there it is. So what was the driving force of our evolution? And one of the big questions is male-to-male antagonism as a driving force of evolution versus sort of larger scale cooperation. And so this is perhaps my favorite sentence in a paper. It's not sentence, but favorite little paragraph, which I will read in its entirety. A frequent explanation of the canine reduction in bipedalism, so canine reduction, it's these guys, like the big sharp bitey teeth, and bipedality is that handheld weapons replaced the SCC, which is like something about like your bite force and how good you are, biting. Handheld weapons replaced the SCC, but if male-to-male agonism had been fundamental to early hominid fitness, what selective agency would have reduced its signature character, how bitey it is? Additional human attributes belie the improbability of the weapons argument. An absence of sperm competition in gorillas and orangutans is accompanied by a dramatically reduced testes size and the elimination of a free scrotum. Their testes are more judiciously sequestered in a postpenial budge. In contrast, not only are human scrota more pendulous than even those of the chimpanzees, but the bipedality makes them extraordinarily vulnerable during upright combat. It seems illogical to attribute habitual uprightness to weapons that would demand even greater selection for testes sequestration than is present in other primates, which basically is to say that the pendulousness of human testes suggests that our evolution at this time was not based off our ability to kill each other with weapons, but must have had some other characteristics, which the paper and sort of a lot of other sources go on to say that it was our ability to sort of communicate with each other and cooperate and sort of work together on things that actually kind of drove the spread of humanity. And I just really love the pendulous testes argument for human compassion present in this particular paper. And there's all this, it gets complex. Ovulatory crypsis, all this stuff. There's a lot of, anytime you get into this layer of biology where people are starting to talk about like male-female interactions, particularly in human evolution, real dicey real quick. Like it's basically, I think, kind of impossible to do this research as a human person and not let the biases of your current moment in social life, like history, shape your explanation. I think that the people who do this well are the ones who sort of recognize that and kind of do their best around it. But you'll see a lot of like people who really aren't qualified using arguments from evolutionary psychology to usually explain why it's okay for them to do whatever they want, which is a classic and long-running human tradition. So after Ardipithecus, you get folks like Lucy. Lucy is a afarensis. Afarensis. Australopithecus afarensis, Lucy. Lucy was oftentimes when you get to this level of, what are you doing? Lucy a afarensis. Is this Lucy? No, that's not. That's Lucy. Why can't I click things? That's Lucy. No. That's Lucy. So Lucy was just a surprisingly intact skeleton, which in this world, this is surprisingly intact. Was around 7 million years ago. She was the first obligate biped. So Lucy spent no time in trees. She spent all her time walking around. She probably could climb about as well as you could if you spent a lot of time climbing. But this skeleton is made for walking bipedally. And then you get to the period of time that I like to call the cacophony of homos, where there was many different hominid species just all over the place. Turns out it's a pretty solid body plan. And this is us. This is Homo neanderthalis, Homo heidelbergensis, Homo erectus, which Homo erectus was the first like bipedal skeleton, which is why they called it that. And then they kept finding older stuff, so it's like the name is no longer quite where it wanted to be. Homo habilis is one of my personal favorites. Homo tool user. We were using tools before this, but they kind of like the names are given at the time that they find the skeleton, and so they find strata in the rocks of like suggesting tool use around this time, and yeah. Yeah, and then they all left. They all died somehow. It's a little bit. That's like another one of the strange mysteries. Is all of our Homo friends died, and it was just us. There's genetic evidence that we absorbed the Homo neanderthalis rather than killing them. They were bigger than us. At a time when we were kind of going through an ice age, so that's a time when big things that have to eat a lot die faster than small things that run around. So there was some evidence that we were hanging out together, and we probably did kill each other a lot, but we also had more productive relationships that led to us being more and them not being around. Yeah.
So like around the time, like 2 million, with all those Homo, like, yeah.
Mm-hmm.
Were there like predator-prey relationships between all of them?
Probably, yeah. It's rough. I mean, because we're talking, so from here back to A. afarensis, this is like 7-8 million years. So this is a long time. And, we're basically in this era, like little bipedal, like, ape men running around with sharp rocks. And we were probably just bashing apart whoever we found, because that's how nature is, So, but we really don't know. So in this era, so we find stone tools from this era, and they also have a cool evolutionary story where the quality of the stone tools progresses kind of linearly, from like, oh, here's a rock in a place that it really shouldn't be. At some point, we kind of figured out that like some rocks are better for bashing than others. And at some point later, we found out that if you smash the rock apart, some parts of it become sharp. And we would find these places where they would like, they seemed to just go find, they had like a chunk of rock that they liked, and when they needed to cut something up, they would just smash it on the ground, pick up the flakes that are sharp, use it for what they needed to do, and then just kind of keep smashing. But there wasn't a lot of plan to it. And then over time, you could see that they would sort of have more and more sophisticated tools coming out, until eventually you get to the point where they're doing like complicated flakes and sort of like breaking it off and having more like coherent stone tools and stone blades, up to the point of like the kinds of like stone tipped spears and arrows that you would associate with like early humans. And then we kind of just got better and better at refining our stone tools until eventually they became things like this. This is a very complex stone tool that we used from smashed apart rocks that we found on the ground. So, Sapiens, yeah. There's this kind of story of like telling the story of evolution is a popular narrative.
Interesting, just like seeing all like the different
Mm-hmm.
humans.
Yeah. Mm-hmm. Yeah, and I mean, we had a pretty big head. I guess I should pull this out before I lose time. So this is Skelly the skeleton, and what is not nearly enough time left. Skelly's seen better days, but I don't know if that part closes. So we have a pretty big brain case, but Neanderthals had bigger. And main part, and I'm not going to have time for this. I'm going to have to shuffle around some class stuff so I have more time to talk about Skelly because I dragged him all the way here from JP. So we'll talk about it in more details, but I will leave you, not entirely leave you, but I will leave you with this. So if you look at, most mammals have a ridge on the top of their skull. So like if you pet a dog, just you'll feel like there's a ridge there. Cats to some extent. Gorilla skull. And most other animals have this thing. Oh, that's called the sagittal crest. The sagittal crest is a muscle attachment point. So the red on this skeleton is tendon attachment, because your muscle doesn't attach to bone, the tendon attaches to the bone. And you can see on the side of the skull, oh buddy, you've had better days, haven't you? I bought this in like a thrift store. I saw it through the window, and I was like, so these things cost, this thing probably cost like $800 new. This one I got for like $300, which I probably could have argued down, but I just feel weird haggling in America, so I just bought it with the price they said. So this muscle attachment here on the side of your skull, like if you put your hand on the side of your head and like squeeze your jaw, like just squeeze your teeth together, you'll feel the muscles moving in your jaw muscle there. And we have a pretty wimpy, bite as far as animals go. That was the whole SCC thing that Lovejoy was talking about. Like we kind of suck at biting for mammals, especially for apes. But if you kind of imagine taking that part of your muscle, that wimpy skull, and push it together until your fingers meet, that's kind of what you get here. So your jaw muscles come from the jaw, they go through your cheekbone, and then they attach on the side of your skull. And so if you're an animal that relies on its bite, you want that attachment point to be, you want those muscles to be as big as they can be, and you want those attachment points to be nice and strong. So we, over the course of evolutionary time, kind of gave up on that strategy. And so now if you kind of imagine one of these, these are all gorillas. If you imagine kind of like taking this and sort of blowing it up like a balloon, you basically get what's left here. So instead of having the really hard, strong attachment points on that top of the head, you now get these kind of like wimpy, diffuse attachment points spread out over the side of the skull, but you get much, much more room to stuff a lot of brains in. And so this is kind of part of that. So this is part of the thing that Lovejoy was kind of talking about, was trying to make sense of us giving up our greatest weapon of strong bites, and then this argument that, we must have done that because we already had weapons. But then the other argument around pendulousness comes in, and that's about where that story ends. Not really ends, but it goes a lot of places, but that's where I'm going to stop talking about it. So I'm running out of time, and I have more that I want to say about the pelvis and the feet and the knees and all that kind of stuff, because in my previous life, I was a locomotion-focused scientist. But I'll leave it here in the sense of talking about the tool use thing and the evolutionary record and kind of this origin of humanity that sort of comes about. And again, that kind of story around where we, like, what was it like to be a human back in the early stages of humanity. And so one of the things that they found was, I think that one of the things that really kind of, for me, gives me the best view of what was going on back then was from the stuff that we could find from the fossil record, which mostly refers to the tools, which were mostly rocks and things like this, and you're getting from simpler stuff like this to more complex stuff like this. But you also find the bones themselves, which are sometimes just kind of, the problem with fossils is that they don't happen very often. You have to have a very specific set of circumstances for a fossil to occur. And so the bones that we find are sort of like random, and things like Lucy are, very indicative of that was a very big find. And there's two kind of, but sometimes you find things like burial sites. And you find burial sites for animals, for other homos that were not us. Things like Homo naledi was a relatively recent discovery, and there was a relatively recent, within the past, I would say, couple of years, discovery of a burial site that they would find, that they would bring their dead to this place, and it was deep in this cave. So they were like these guys, which were basically like little, like tiny little monkey men, or monkey folk, I suppose. Were taking their dead down into this cave and putting them in a particular chamber for some reason. What would they probably didn't speak English, but they had some reasoning for it, and they would go back to it. And we would find animals, and particularly once you start talking about Homo sapiens, which the modern Homo sapiens sort of shows up around 200,000 years ago. So anything from now to 200,000 years ago, you pick one of them, you put them here, raise them in a good school, identical to us, genetically the same. So we find bones of old Homo sapiens and old Homo neanderthalis, and sometimes we find them in burial sites, but we also would find them, they were always busted up. Like, they hurt themselves a lot. And one of the primary human superpowers, apparently, relative to other animals on the earth, is our healing factor. Like, we heal very, very effectively and very, very fast relative to most other mammals. And this is of note because if we've ever known anyone who has broken a bone, healing really fast from a broken bone is still kind of slow. Like, it still takes weeks and months before you are up to speed again. And we would find old skeletons here covered in broken bones. Like, they broke their bones all the time. They lived very rough lives. And if they had broken bones, and if they were still surviving to adulthood, that means that somebody was taking care of them. When they were injured, they weren't thrown out because they weren't useful. They were cared for and nursed back to health. And there's some, I wish I had more details on this, but there are some cases where they would find skeletons of old homos that were like twisted, like the limbs were twisted and not straight, as if they were born with a bone disorder. But the creature that had that bone disorder still survived to adulthood, which means that somebody was taking care of them. And they took care of them for years. Whoever they were not pulling their weight in terms of like hunting and gathering. So if they were able to survive to adulthood, it's because someone else in their clade found more value in them than what they could bring to the table in terms of their raw physical capacity. We would also find things like, sometimes you would find these kinds of rocks, and they would be made out of things like rose quartz, just like rocks that are not necessarily good for tools, but they were just like pretty. And we apparently we like pretty rocks. And so they would find these rocks, but they wouldn't find them out and about. They would find them in burial sites. So someone had a hominid friend who died, who had their favorite rose quartz, and rather than taking this rare special rock with them, they put it in the ground with their dead friend. And I think that is something, in this last 30 seconds of class, it's something I go back to think about things like that a lot. And I think about those origins and that kind of story, and what that says about like whether or not we have any hope in the present moment. Because there's a lot of stories that people like to tell around how harsh and horrible and rough it is in the world, and how only the strong survive, and empathy as weakness and things like that. But it's really not. Like, if you go deep down into the bones of the fossil record empathy is the original superpower that allowed us to sort of take down mastodons and survive extinction events and sort of make it to the place that we are today. So I think I am, I guess, legally obligated to leave it at that. I will bring this guy back out at some point in the future so I can talk about what C.L. Lovejoy called the most phylogenetically distinct osteological structure in the animal kingdom, otherwise known as the pelvis. Not the skull, the pelvis. But other than that, I will leave it at that. And I hope I was able to scrape that back to something resembling relevance to the current topic. And I hope that's not the only time you look into that story, because everything that I just said is just little tidbits that you really should pull those threads. Talk to the bot, Google around about it. Whatever thing I said that you're like, oh, that's interesting, dig in, because there's a lot more there. And I guess this class is supposed to be about how to become like a real scientist type person. And to do that, it means joining that conversation and joining it in the context of the full story. So we'll leave that there. And